Chapter 4, Module 1. In this module, we shall discuss quotient spaces and quotient maps. Another name for quotient space is identification space. Construction of identification spaces from a given topological space give methods for obtaining various topological spaces from given ones. We shall see that apparently complicated spaces can be viewed as quotient spaces of very simple looking topological spaces. We introduce quotient spaces by looking at an illustrative example. Consider a rectangle X. The rectangle contains the points x, y, where x varies between 0 and a and y varies between 0 and b. Here a and b are real numbers greater than 0. Now, we partition the points of x as follows. We take the points on the left vertical edge of the rectangle, call the point 0 y. We take it with the same set as the point a y, which is on the right edge of the rectangle. So, that means we are taking the points 0 y and a y in the same set of the partition, where y varies from 0 to b, and any other point of the rectangle will be in the singleton set x y. So, that means we are identifying the opposite edges of the rectangle and we obtain a new figure which is actually a cylinder. If C denotes the collection consisting of each member of the partition, then we can define a natural map pi from x to C, which is described by the point x goes to the point x bar of C, where x bar is the set which contains the point x. Since it is a partition, x belongs to one and only one member of C, and therefore, this mapping pi is well defined. Now, we use this map to topologize C as follows. We assign the largest topology on C, which makes this function pi continuous. That means, a set O is open in C if and only if pi inverse O is open in X. This particular topology is called quotient topology or identification topology on C. Now, it is worthy to mention that a partition gives rise to an equivalence relation. On the other hand, an equivalence relation always gives a partition which consists of the disjoint equivalence classes. So, in the explanation above, one may use an equivalence relation instead of a partition. Following are two very important observations about this map pi and the topology that we have already defined here. First of all is that the quotient topology on C is same as the subspace topology on C induced from R3. This result follows from looking at the basic open sets of C as a subspace of R3. We know that the basic open sets of R3 are the open balls, and when it is intersecting with the space C, it is giving back the open sets of C, rather the basic open sets of C. So, the basic open sets in this case, when C is a cylinder, will be the opened disks drawn on the surface of the cylinder. The second observation is very important, that pi, which we have defined from x to C by mapping the point small x of capital X to the set x bar, which contains the point x, is not an open map. We observed that the function pi was defined from x to C, and the topology was such that it takes precisely the open sets of C back to the open sets of x. That means that it cannot pull back any other set to an open set of x, but that does not mean that it will take an open set to an open set of C. Here is one illustration. If we take the half disk D containing the points x, y from capital X, having center at A b by 2 and radius b by 4, then that is surely an open set in X with respect to the subspace topology induced from R2. But if we take pi of D, the image of D under the map pi, then once again we will get this open half disk drawn on the cylinder. Now, pi D is not open in C with respect to the subspace topology induced from R3. So, that means pi will not be an open map. Now, we generalize the construction involved in this illustration for any topological space X instead of a rectangle on R2. Let us take a topological space X and an equivalence relation rho on X. We take all the points x bar, where x varies over capital X, where x bar stands for equivalence classes of the relation rho, and on this x bar we want to define a topology. So, we define the function pi as usual from capital X to x bar by the map which takes the point x to x bar, where x bar is the class containing the point x. The quotient topology on x bar is the largest topology that makes this function pi continuous. That is, any set O is open in x bar if and only if pi inverse O is open in X. The space x bar is then called quotient space or identification space of capital X. Let us go through some examples. The first example shows that we have started with an unit circle S1. We want to show that this circle S1 is a quotient space of the closed interval 0, 1, where the partition is given by the points, rather the sets singleton x for every x within 0 and 1 and a 2-point set 0 1. That means, we are starting with a line segment from 0 to 1. In the diagram, we take a line segment from 0 to 1. The points 0 and 1 are drawn in the figure by red dots. This identification says that we are gluing these two red dots together. By this identification, we are going to get a circle where the only identification is made on the two dots to form a single dot on the circle. In the next example, we see that a 2-sphere is a quotient space of the unit closed disk D2, where the partition is given by each singleton xy, which represent the distinct class when the point is not on the boundary circle. And secondly, we take the set of points on the boundary circle which represent a single class. The quotient space obtained by the above identification is a unit sphere. As one may expect, very naturally, changing the partition, we may get different quotient spaces from a particular space X. For example, we take the closed unit disk D2 and consider the partition consisting of the sets as follows. Each singleton xy, which represents distinct class when the point is not on the boundary circle, and when the point is on the boundary circle, we take the points xy and its diametrically opposite point -x -y in the same class. So, the quotient space of D2 determined by the above partition is called the real projective plane RP2. Here we see that the partition is different from the one which we have explained in the last example, and therefore, the quotient space obtained is totally different one. Previously it was a sphere, but in this case it is projective plane. Now, we recapitulate a few figures which are very well known topological objects. The first one is the real projective plane. The second one is a Mobius band. Third is a torus, and the last one is a Klein bottle. In the previous example, we have seen that a projective plane can be obtained from a rectangle by some quotient topology. We shall see next how we can obtain the quotient spaces Mobius band, torus and Klein bottle from a rectangle by changing the equivalence relation. Mobius band as a quotient space of a rectangle. Let us see how we can get the Mobius band. We consider the rectangle X containing the points x, y from R2, where x varies from 0 to 1 and y varies from 0 to 1. We take the partition as follows. We take the rectangle, take the vertical edges of the rectangle and identify the left edge with the right edge, but in a reverse direction. That means, the point 0 y on the left edge will be identified with the point 1 minus y on the right edge. So, taking a rectangle and identifying two opposite edges of the rectangle, we are obtaining the Mobius band, but while identification we are giving a twist to the rectangle. In this example, we see how torus can be obtained from a rectangle. We consider the same rectangle and the identification is made as drawn in the figure. The left edge, left vertical edge is identified with the right vertical edge along the direction of the arrow, and the upper edge is identified with the lower horizontal edge along the direction of the arrows. So, first of all we are identifying the upper edge with the lower edge, that is shown in the second partition, that x0 and x1, these two are inside the same set in the partition, and when we are saying that we are identifying the vertical edge with the other vertical edge, that is seen from the first partition, where 0 y is identified with 1 y, y belonging to closed interval 0 1. That way, keeping the rest of the points fixed, that means no other identification is made, we get the torus. Now, in case of real projective plane, we take the same rectangle, but in this case the identification is exactly the way it is drawn in the rectangle. We are identifying the point 0 y with 1 minus y. That means, while identifying the vertical edges, rather gluing the vertical edges, we are reversing the direction, and same thing is done for the horizontal edges. While gluing the lower edge with the upper edge, we are using a twist again, and the rest of the points are kept single. That means, they are not identified with any other point and thereby give real projective plane. For Klein bottle, we do the same thing, but the identification is a little different. Here the points 0 y and 1 y are identified for each y belonging to the closed interval 0 1, and the point x0 is identified with 1 minus x 1 for each x belonging to the closed interval 0 1, and the rest of the points are kept as it is. This is how we get Klein-Bottle as quotient space of a rectangle. We have seen that the function pi is playing very important role in construction of quotient spaces. We now generalize the behavior of that function pi to get the definition of what we call a quotient map. Suppose Y is a quotient space defined from capital X and Z be any topological space. A function f from Y to Z is continuous if and only if f composed pi is continuous. If f is continuous, then the composite of two continuous functions being continuous, f composed pi is continuous. For the converse, let us start with f composed pi and suppose that it is continuous. We choose any open set U from Z, then pi inverse f inverse U, which is equal to pi inverse composed f inverse of U, which is f composed pi inverse of U, is open in X. Since f composed pi is continuous, f composed pi inverse of U is open in X, and therefore, pi inverse f inverse U becomes open in X. Now, the definition of quotient topology says that pi can take back only the open sets of Y to open set of X. Since the pulled back portion is open in X, f inverse U must be open in Y. Therefore, f is continuous. Now, we define a quotient map. Suppose x and y are two topological spaces. A surjective function f from x to y is said to be a quotient map or an identification map if it has the property that it pulls back precisely the open sets of y to open sets of x. That means, f is a quotient map when O is open in y if and only if f inverse O is open in x. This condition is satisfied. We now see this theorem that if f is a quotient map from x to y and g is any function from y to z, then g is continuous if and only if g composed f is continuous. To prove this theorem, we can see that the proof actually follows exactly the way we have proved it for the function pi. Previously, we proved this theorem when the function f is taken as the function pi, and we have used the property of pi that it satisfies the condition that O is open in y if and only if f inverse O is open in x. Another description of a quotient map can be given in terms of saturated open sets. Suppose P is a surjective map A subset C of X is called saturated if C contains every P inverse Y that intersects C. That is, for all Y belonging to capital Y, either P inverse Y is contained in C or P inverse Y intersection with C is empty. A function f is a quotient map if and only if f is continuous and fa is open in Y whenever A is a saturated open set in X. It is natural to ask why such a function f is called a quotient map. The name is justified in the following result. But before stating the result, we observe certain obvious facts. Let f from x to y be any function. Take y bar as f inverse y, y belonging to capital Y. Then for each x belonging to capital X, there exists some y belonging to capital Y such that x belongs to f inverse y. And secondly, f inverse y1 intersection f inverse y2 is empty whenever y1 is not equal to y2. So, capital Y provides a partition of capital X which gives a quotient space of capital X. We see in the next theorem that if f is a quotient map, then this quotient space y bar of capital X is topologically same as capital Y. That means, we state the theorem formally, let f be a quotient map, the quotient space of capital X determined by the partition y bar containing the fibers f inverse y, y belonging to capital Y is homeomorphic to capital Y. The following result helps to find whether a given map is a quotient map or not. But one must be very careful about its use because the converse need not hold in general. If a function f is surjective, continuous and an open map, then f is a quotient map. How do we prove it? We take an open set O from Y. The continuity of f says that f inverse O is open in X. Now, conversely, we start with an open set O such that f inverse O is open in X. Then it is given that the function f is open. So, f of f inverse O is open in Y. Function is surjective and therefore, f of f inverse O is O. That is, O is an open set in X, which proves the requirement. Now, as a corollary to this result, we have that if f is a surjective, continuous and closed map, then it will be a quotient map. If f is a continuous surjection from a compact space capital X to a Hausdorff space capital Y, then f is a quotient map. In view of the previous corollary, it is enough to show that f is a closed map. So, we start with a closed set C from X, C being a closed set in a compact space capital X, it is compact. Therefore, the continuous image F C is compact in Y. Once again, compact subspace of a Hausdorff space is closed, and therefore, F C is closed in Y. That means, F is a closed map. Therefore, using the previous corollary, we have that F is a quotient map. So, in this module, we have seen the construction of various important topological objects such as projective plane, Klein bottle, Mobius band, torus, etc. as quotient spaces of rectangles. In the next module, we shall see various other techniques of forming quotient spaces from rectangles. With this note, we end chapter 4, module 1.